Welcome once again, and we are continuing our discussion on interior point methods. Yesterday we started our discussions, gave a very basic idea of what we are supposed to do, and we wrote down the KKT conditions, and we are just attempting to now solve the KKT conditions, because solution of a KKT conditions would give me the required minimum. In fact, the KKT condition solves two problems. By solving the KKT conditions, I not only solve the primal, I also solve the dual. So, these methods that we will soon start doing, they are called primal dual interior point methods, because they are jointly solving both the primal and dual interior point, because they remain inside the interior of the feasible set. Now, let us observe that if I look at the KKT conditions in the page before this one, I can write it down in a more standard equation form. That is, I can write this KKT condition as a system in this form. A transpose this, I will very soon tell you why I am writing this, where x and s are greater than or equal to 0. X, when you have a vector x and you are writing a corresponding capital X, this symbolizes a diagonal matrix whose diagonal consists of all the elements of the vector x, all the components of the vector x, and this S is also a diagonal matrix consisting of all. Now, an E is the vector 1 1 1, and of course, you can see that x s E is nothing but the vector is nothing but the vector x 1 s 1 dot 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 x n s n, because all of them are equal to 0, right. That is a complementary slackness condition. So, this is in R n, this is in R m, this is in R n. So, basically my vector is in R n plus m plus n, which is also R to n plus m. So, any element here, any element of this form can be viewed as an element here. Of course, it is an element in this space R n plus m plus n, that is, or R n cross R m cross R n. Now, I have to solve this equation, and what do you mean by Newton's method for solving this equation? Newton's method we have learnt also in calculus, right. Newton's method comes in the very first course in calculus, calculus 1 in most of our engineering colleges, most of our universities. When you learn calculus 1, you learn Newton's method. Newton's method here is, so what we are going to look into is a function f from R n to R n, and we are going to try to find out, find an x. So, if I have this equation, my question is to find an x such that f of x is equal to 0, such that this is occurring. Now, the Newton's method that you learn in the first year of your studies is for a function from R to R, where n is equal to 1, and there you have f x equal to 0. If you take up your calculus books, you will see that this Newton method works on a iteration scheme given as follows. The k plus 1th iteration is given in terms of the kth iteration as So, x plus x at the k plus 1th iteration is the kth iteration x k is the kth iteration x k minus f x k by f dash x k. So, I can write it bit more cautiously. F dash x k inverse s to the power minus 1 into f x k. Now, when I have the situation from f from R n to R n, can I write down the Newton's iteration scheme? In this case, I have n and my derivative would be nothing but the Jacobian. See that here the derivative is not equal to 0, because here if the derivative is 0, this will be meaningless, right. This is of course, we are trying to find for a differentiable function. These are all differentiable functions. This is something I should have mentioned. So, these are all differentiable functions. If you look at the function that we have written down for the KKT scheme, that is also a differentiable function. Now, how do I look into this thing and try to how do I look into this iteration scheme for R to R and try to get an idea for R n to R. Now, here you can use your intuition. Of course, I would leave you to mathematically actually rigorously write down the scheme, but let us just use for fun use the intuition. Now, for this the derivative is nothing but a Jacobian mapping, and we assume that there is an inverse and then f of x k. But who told me that the Jacobian would have an inverse? That is the whole question. So, how does, so if I write it much more, if the Jacobian was not having the inverse, then possibly I could have written the whole thing down in this fashion. So, this essentially is the Newton iteration scheme. So, this is the basic Newton iteration, and this one is when the Jacobian has an inverse. The Jacobian matrix has an inverse. So, when you have functions from R n to R n and R is bigger than 1, n is bigger than 1, then your derivative becomes the Jacobian matrix. So, I am sure that you have heard about Jacobian matrix in your basic calculus courses. So, what you take if you look at this function f. So, let me just give a little bit idea about the Jacobian in case you have forgotten it. So, you take this function f x, say let it say R 2 to R 2. So, you have f 1 x, you have f 2 x. Now, the Jacobian j f x is nothing but you write the gradient vectors as row vectors, grad of f 1 and grad of f 2, write them as row vectors and put them as rows. So, that is exactly your Jacobian matrix. Now, once I know this, how do I adapt this thing to my own system, of Karush-Kuntakar inequalities? So, for our case it would be like this: the Jacobian of f at x, our case, let me emphasize it is our case now. So, we are applying the Newton scheme in our system. Now, x k plus 1 minus x k minus 1, I should have written x k, okay, I will write x k. If you are not convinced, it is better to write x k and then later on make it much more simpler. So, let me write the scheme. Jf xk yk sk, this thing multiplied into this vector now xk plus 1 minus xk, yk plus 1 minus yk, and sk plus 1 minus sk, and this must be equal to minus f of x y s. This is your Newton scheme for KKT conditions. Of course, you have to have that what is that called, that x and s has to be greater than 0. This is something you have to keep in mind. So, this is the Newton scheme for KKT system, but there is something interesting. Now, if this would be k, I had made a mistake, this is xk yk sk, right. Now, so if xk yk and sk is in the strict primal feasible cross strict feasible strict FDE, or the equivalent problem, then what would happen? This yk sk is actually here. Then what would happen? Then how do I write down the KKT system? Then the Newton scheme becomes and that is what we will have in most cases, because we will have a feasible point which is in the interior. Now, that would allow us to simplify the Newton scheme, and the Newton scheme would now look as, so I will just put delta xk. So, this difference is I will write as delta xk, this difference I will write as delta yk, this difference I will write as delta sk, and this. So, once I have this would tell me this is nothing but, because it is, so Ax is equal to b and A transpose y plus S equal to c. So, 0 0, but only thing you would have is that this I do not know what will happen, because it is strict, the product is of course something. So, now this is the equation I am supposed to solve. This is the, so if I solve this equation, so my new xk plus 1, once I solve del xk, del yk, del sk, if I find these values, then xk plus 1, yk plus 1, sk plus 1 can be found by this following line search iteration scheme, which is xk, yk, sk. Sometimes what is done, we just do not add this to del xk, though we have made that to be the sign, you can actually add these things. But sometimes from the point of view of practice, it is useful to have some additional parameter. So, this is giving you the Newton direction, right. These solutions of these are called Newton directions of the KKT system. But then, so if I perform a line search along the Newton direction for some search parameter, I will take alpha between 0 and 1, oh sorry, 1 is included. Then I have to see what would happen, that if I just join this to xk plus del xk, I might get a point which might not be strictly positive. That is the whole point, it can be in the boundary. The idea is to restrict it inside the feasible set, and as a result of which what we have to do is to take this controlling parameter or line search parameter. Now, once I know this, I do this because what I want at the end is xk plus 1 to be strictly bigger than 0 and sk plus 1 to be strictly bigger than 0. So, this alpha has to be chosen in such a way such that this holds, and the whole game is how to solve this system. How do I solve this system? So, the whole emphasis in interior point methods is to try to solve this system. So, this will lead us to the story of the central path. So, what we do is that instead of solving the exact KKT system, we would like to solve something called a perturbed KKT system, which we would write down, and let us see. So, instead of solving the exact KKT system where I have xi si equal to 0 for all I would try to solve the following system. Xi si, I said this is equal to tau, that for every xi si it should be a number tau, though it is not so easy to find something which will do it. So, in that case that would give us what is called a central path. So, if I solve this system of equation, what I would get is something called a central path. I keep on changing the tau, and what I do is I get a central path. So, I have this feasible polyhedron and I get a central path, which is all the points lying on this path is solution of this system. But when I actually solve this system, I do not get the exact points, I get something nearby. But these nearby points, which are the approximate solution of this system, cannot be too far off from this central path. It has to be somewhere quite near to this central path, and so we will see that we will define certain neighborhood which will push those points in a tube along tube or some sort of set, which will keep the whole points, the iterates, within certain region of the central path. So, gradually we will force them towards a solution. Now, instead of doing all these things, you might ask me a very important question. Now, you have this particular system for the KKT thing, that is, I have written here 0 because I have assumed this, because if you had written here this minus fxk thing here, this would become minus A transpose yk plus Sk minus Ck A x k minus b, and of course, I am not writing it x s e. I am not writing the details, but now, so what I am trying to say is that you might ask me, in that part you said that okay, this is the scheme that you write when you do not have differentiability, but if you are in the interior, will this be differentiable? Well, sorry, will this be invertible? I am writing this scheme when this Jacobian matrix is not invertible. Now, the question is, will this particular Jacobian matrix, when I take the Jacobian of this map, will it be differentiable if I take that fact that xk, yk, sk comes from this set, and that surprisingly turns out to be yes, and that is one of the major results of this whole area. So, this is a very brief idea of this central path which we have given. Now, we will get into a more important issue. We will first write down the following important result. Though we have not done the central path yet in complete detail, we have not done the central path yet in complete detail, but we are going to write the following important result. The Jacobian this is given by this matrix. It is a homework for you to figure out that this is the correct answer. This is the Jacobian. Now, J f x y s is invertible if x is strictly greater than 0, s is strictly greater than 0. This is very simple. This is very simple, this whole proof. So, I will again leave this as homework to you. Now, before we deal with central path in so much details, it is important that we look into this problem slightly more historically. See, the interiors writing an algorithm being in the interior of a feasible set is not a very new concept. It is a very old concept, and you will find in the very old book by Fiacco and McCormick. And what happened is that they devised what is called the barrier method, and this barrier method was a nice interesting idea, where the points which are in the interior are not allowed to move towards the boundary. That is, if you are moving towards the boundary, the function value would they create a function called the barrier function, whose value would start going towards plus infinity. So, and that is, so you would lose interest in minimizing such a function, because your idea is just like the penalty function. You create a barrier function by combining the constraints and the objective, but you do it in such a way that your iterates at every stage as you solve the sequence of barrier problems are inside the interior of the feasible set, in contrast to the penalty method where you have it in the outside. So, now I am talking about penalty method etc., which I have not spoken about, which could be in a separate course, but you need not get too much worried about it. What I am telling is that there was this historical method, it was around 1960s or I guess 1966 or something like that, if I am not very wrong. So, this people lost interest in this idea completely. It was a theoretical idea with a nice convergence proof, everything, but suddenly when interior point methods were being looked into after Karl-Marx's revolution, when people started looking more deeply into the interior point methods, many researchers like Michael Todd, Jim Renneger, they figured out that there is a deep connection between the barrier method and the Newton scheme. So, the barrier method will play an extremely fundamental role in interior point methods for linear programming. So, we will define what is called a logarithmic barrier function, and we would like to show that this barrier function is intimately linked with the solution of this Newton system of equation or the solution of the KKT system. So, it is intimately linked. So, barrier method is linked to it. So, if you optimize or minimize a barrier function in this particular case with certain barrier properties, with certain type of barrier functions, you are actually solving the KKT system. So, it is very important that this link be established, because this is a deep link and this actually illuminates the whole mechanism of this interior point techniques, because the barrier methods were the first class of interior point techniques. So, our standing assumption now, you might say that, oh, what are you writing, this could be phi, this could be empty. Yeah, you can figure out examples that this could be empty. I will not give you the example right way, I will give you the example after I do a bit of the subject. So, for this current moment, let us assume that you have these things given to you, and now we are trying to build up this link with the barrier function. So, we have something called a logarithmic barrier function. You will understand why it is called logarithmic barrier function. Because you have a, so for all x in the feasible set, all x in f naught p, define the function so this is a constraint, and then the x greater than equal to strictly greater than equal to 0, that constraint is pushed into the ln means log natural. So, if you are getting confused, ln x is log to base e. So, xi's are all positive because I have taken them from the strictly feasible set, and this is my logarithmic barrier function because I have used a log. So, this is what is called the log barrier function. So, usually it is known in the literature as log barrier function. Mu here is called the barrier parameter, and mu is strictly bigger than 0. So, it is important that if I want to optimize this problem, I would like to know its gradient and Hessian, because that is what is done in standard optimization problems, that you, because you will do unconstant optimize, not really unconstant optimization, but you are basically looking at these problems because you want to solve this problem over this particular set, which is an open set because you are in the interior of the feasible set, you cannot be on the boundary. So, this is an open set. So, it will be just same as unconstant minimization. Now, if you optimize over whole Rn and optimize over an open set in Rn, your optimality conditions are same. Of course, it is not so simple to say that okay, optimality conditions are same. How they are same? That would again involve in one to more deeper discussions about the geometry of the sets, the associated tangent and normals, and so we will not get into all these things, but just listen to the following thumb rule. If I have an open set in Rn, my optimality conditions are just like unconstrained ones. Now, I also want to determine the nature of this problem, whether it is convex or not. This is convex, of course, this is also convex. So, this problem is convex. So, what sort of convex is it? Is it strictly convex or strongly convex? So, some better property than just convexity. So, you see here I would have what is x inverse, because here all the capital X is the diagonal matrix consisting of x1, x2, xn, on all these elements are positive. So, x inverse is nothing but a matrix of this form. That is all. And of course, you can see figure out this one. So, you can figure out this at home at your leisure time. So, this actually means nothing but x1 square, x2 square. So, this is PD, positive definite. So, this Hessian matrix is positive definite on f naught p. So, this shows that this function, again go back to your old notes, our very beginning studies, that because of this is a positive Hessian is positive definite, this function is strictly convex. So, phi is strictly convex on f naught p. So, our conclusion here is the log barrier function phi mu is strictly convex on f naught p. Now, what about the dual function? So, now the next natural question is what about this dual problem? Can we construct a barrier function for the dual problem? The answer is yes. So, let us construct a log barrier function not for dPe, but for dP, just because that is where the strictness comes in. So, you will have something like this. Why is because we are talking about dual variable, this is the dual objective. here we add and not subtract, because we write it in that form, because I have written ln of Ci minus aiy. Ai is one row vector, ai is the here aiy is a vector denoting the first row of the matrix A, sorry, the first column of the matrix A. So, it is A transpose y is, if you compute out A transpose y. So, A transpose means if you multiply, so the first column, the ith column of A, the ith column of the matrix A is denoted by ai. So, if you do A transpose y, if you compute out this matrix consists of the, if you compute out this matrix computation, this is a vector A transpose y, and this A transpose y is a vector which whose ith position consists of this particular real number. So, but this is strictly less than Ci, because y is a dual variable. So, for all y in f naught d, I have defined it like this: I is from 1 to n, okay. But there are n columns. So, ai, a1, a2, an are n columns of the matrix A. Okay, that is it. Now, what about this guy? Does it have anything to do with, does it have any nicer properties like convexity and all those things? Okay, let us compute out this. So, this will give me something of this form, which you can compute out now. This is negative definite, because if you look at this one, these matrices, this mu is positive, and if you look at these matrices, and because y is positive here, this is positive. Now, ai transpose, these are because of course, I am assuming that ai is all of them cannot be 0. The AIs are, some of the AIs are non-zero. So, the rank assumption tells us that using the rank assumption that rank of A is m, you can actually prove that the product that this matrix is negative definite. So, prove this in the homework, prove grad square phi tilde mu y to be negative definite on f naught d. So, this is okay. So, these are some facts which let us keep. Now, what is the relation between these barrier functions and the KKT conditions? Let us just have a look, and we will try to end our discussion today with this very fundamental theorem, and we will start our discussion about the central path tomorrow, and also about that, also we will discuss a bit about the primal dual framework and all these things. So, and how to exactly solve the Newton system, we will give you the exact solution of the Newton system. So, here we are not going to prove each and everything which is not feasible because of the time constraint in this course. So, we are not going to prove each and every step, it is not possible, but give you the major ideas, because here you know you are putting in some sort of a small capsule, because the interior point is a whole course. You can the proofs will take quite a bit of time. So, some proofs would be given, not every proof, and but here we will state the fundamental theorem, fundamental result on barrier functions. But we will not prove it. See, what would happen is that proofs of this would require certain sophistications which might not be available with all it would need mathematical sophistications which might not be available with all the audience seeing this course. So, keeping in view the keeping in mind the viewpoint of all the audiences, I would like to emphasize that all results now will not be given a proof, like we were giving in the very first part, the very basic part, that we are giving proofs of everything, but here we will not be giving proofs of everything. We will emphasize the results, certain smaller results, etc. Of course, we would be proving, but not each and everything. Our idea here is not really to show you that, okay, come on, how do you solve the, or how do you numerically write the algorithms, but give you a very brief idea. So, we will not write down each and every algorithm, we will write down one basic algorithm through which we can test the theory that we would develop now, but then we would also give certain more algorithms, we will tell their references and you can go and have a look at them. So, let us write down this fundamental theorem to end this course today. So, let us write down the following facts. So, these are non-empty, this is known to you. There exists, of course, there will be unique minimizer, because it is strict minimum. If there is a minimizer, that should be unique. Maximizer. So, you know, I just want to remind you that this one what you have got here, this one, this shows that this function is actually concave, not convex, but concave on f naught d. So, you have to maximize a concave function. So, dual problem is always a maximization game. Sorry, f naught p, this is f naught p, this is f naught d. The system instead of tau, let me put some, it will be f mu, I will write as f mu. See, what would happen is that here we will show that if I can minimize the barrier functions, I am actually minimizing this problem with this equal to mu. So, if I fix up a mu and if I minimize a barrier function, then I am actually finding a unique solution of this system of equations, and that is the important connection, because this is what we want to solve. We are not hell bent in solving the KKD condition, but we have to solve this approximate condition, and that is very important for us. From the practical point of view, this is what we have to solve, because we have to be in the central path. So, the as solution of the barrier method, the barrier functions leads to the generation of the central path. So, that is the beautiful theoretical link. Okay, we will try to give a little bit of proof for this one because this is very fundamental. So, XS X capital S, sorry, or you can write XSE. So, this actually means x1 S1 equal to mu, x2 S2 equal to mu. Here I could also write this part, this last part, see XS mu e can be written as XSE minus mu e, same thing, does not matter. So, this so let us have these 4 conditions written down, 4 as a things, 4 statements. We have made 4 statements and now we are showing that A implies B and B implies A, B implies C and C implies B, and hence C implies A and A implies C. So, what we say is that all the above 4 conditions are equivalent. That is, if I can solve the log barrier function, then I am also solving this system. Give me the mu. So, once you know that if there is a solution to the log barrier function, if there is a solution to the unique dual, so what happens is that the solution to the log barrier function and the solution, if you have a solution to the log barrier function and when you have a solution to the minimizer of the log barrier and maximizer of this dual log barrier for the dual one, then you are solving this. So, or if you just know that you have found a minimizer on this one, you know that there is a solution to this. So, a solution or the existence of the central path is intimately linked to the solution of these 2 problems, that is minimizing phi mu over this and maximizing phi tilde mu over f naught d. So, this is a very important thing. Maybe we will give a scheme of the proof of this tomorrow and then we will move on to the central path and other related issues. So, the idea, as I told you again, is to move along this central path, start from a point in the inside and start moving along the central path. So, if each point on the central path is a unique solution of this system, but the question is that it is very difficult to solve this system. So, then our idea would be to solve it approximately, but still solve it in such a way so that I remain near the central path and I can make one step ahead. So, but how do I know? My idea is that I will have to force this tau to go to 0. I have to force this tau to go to 0. So, at every step I have to whatever xi si I compute the approximate ones, one has to compute this sort of control parameter like this, which is called the duality measure. Basically, I would like to force this duality measure to go to 0. Basically, from a just very simple point of view, I am forcing this tau to go towards 0. If as I make tau smaller and smaller, I keep on, if suppose this is the solution, then I keep on moving along this central path and go and hit the solution. That is the basic idea. And so, tomorrow we will start with some brief idea about the proof of this fundamental result on log barrier functions and the approximate KKD system, and then we will go into the other issues. So, we will have I will have some 4 or 5 more lectures on this whole thing. So, we can take it slightly easier and then we will go on to semi definite programming, which is almost the end of the course. So, we will basically have learned 2 very important class of convex optimization problems, their algorithms, their deep properties, and you will see that semi definite programming is so important because lot of things come under semi definite programming problems. Lot of problems can be modeled as SDP, which cannot be modeled as linear programming problems. So, thank you very much, see you tomorrow.